Hello everyone. In this practice hackathon, our objective was to develop reliable classifiers that maximize the F1 score for predicting law of default while ensuring that the model is proper, felt, and validated. So the dataset contains 36,000 training observations with a positive class rate of about 22%, meaning the database is moderately imbalanced. So our final Kaggle public leaderboard score was about 0.8628. Achieving use of band model combining light GBM and CatBoosting, um, along with the target features engineering, class imbalance handling, and the threshold optimization. So the first thing we did is feature engineering. We did not rely on solely on raw material provided in the dataset. Instead, we engineering several features designed to better reflect the financial risk structure. First, we apply log transformation to score variables such as income, loan amount, um, interest rate. This helped the tree-based model better handle heavily tailed distributions. Then we create a risk ratio feature such as loan to income ratio, payment process, loan amount times the interest rate divided by the income. All these features directly capture the repayment burden, which in economy the meaningful for predicting default. And then we add on interaction features such as interest rate, um, multiple by loan amount, and the credit score multiple by the credit history length. So all this allow the model to capture nonlinear risk relationships. Finally, the categorical variables like education level, loan intent, we apply out-of-fold target encoding with smooth. This preserves the predictive signal while avoiding the data leakage and reduce the dimensionally problems of the one-hot encoding. And then goes to the multiple models. The logistic regression and random forest, like GBM and CatBoosting. For logistic regression, it was served as a baseline, and for the random forest, improved the nonlinear modeling, but did not perform as strong on the imbalance data compared to the gradient boosting methods. For the light GBM, it performed significantly better. It handles structured tabular data very efficiently and support class weights. Um, for the catalyst, perform similar but slightly different from the light GBM, and especially in handling categorical features because the light GBM and CatBoosting learn slightly different decision boundaries. We band them predictive probability using weight averaging, and this ensemble approach consistently improve the F1 score over the either model alone. And then handle the class imbalance since only 22% of the observation belongs to the positive classes. We apply two strategy. The first is class weighting during the training, and the second is threshold tuning after training. Um, for the first one, for the second one, instead of using the default decision threshold of zero point 0.5, we searching for threshold that maximize the F1 score and auto-fold prediction. The optimum threshold turns to be 0.609, which significantly improve the F1 score compared to zero point 0.5. And then for this step was critical because F1 score is sensitively to the imbalance between precision and the recall. And then for hyperparameter tuning for light GBM, we tune the learning rate, number of lives, minimum data in live, LTO regularization, features and backing fraction. We use the early stop with five-hole crossing validation to prevent the overfitting and determine appropriate boosting RAM for catables. We tune the dips, learning rate, LTO regularization, and performance improve notably after tuning compared to default parameters. And I will hand it to my teammate to talk about the pump 2 that we use.
about prompt 2, what did we do to access or improve the fit of our classifier? The first one we do is the validation strategy. We use the stratified five-fold cross-validation rather than a simple train test split. And this ensures that each fold preserves the class distribution and reduces variance in performance estimates. We also used out-of-fold predict probabilities to compute F1 score, confusion matrix, and precision recall curves. This approach improves performance stability and reduces the risk of overfitting to a single validation split. And the second is learning curve. I plotted training and validation log loss curves for LightGBM. The learning curve shows that the training loss decreases steadily while validation loss stabilizes without diverging significantly. This suggests that the model is not severely overfitting. To further control overfitting, we used early stopping, L2 regularization, and minimum data in leaf. And the third is a confusion matrix and precision recall curve. I analyzed the confusion matrix at a chosen threshold of 0.609. In long setting, false positives means rejecting good borrowers, which reduces potential interest revenue. False negatives meaning approving risky borrowers, which leads to financial losses from default. Because default losses are typically more costly than rejecting safe applicants, the threshold should not simply be 0.05. The precision recall curve helped visualize the trade-off between identifying risky borrowers and avoiding unnecessary rejections. Adjusting the threshold allowed me to maximize F1 score while maintaining a reasonable balance between risk and opportunity. And if I had more time or resources, I'll do the rest of to start with, external data integration. I would incorporate external macroeconomics variables such as unemployment rate, inflation, interest rate trends. These micro indicators influence default risk and could improve predictive accuracy. Additionally, richer credit data would significantly enhance model performance if available. And the second thing we do would be advanced model techniques. I would implement Bayesian hyperparameter optimization and stacking instead of simple weight averaging, and probability calibration methods such as isotonic regression. And third would be production monitor and data drift. If deployed in production, I would monitor feature distribution shifts, changes in predicted probability distribution, realized default rates across borrower segments. If drift is detected, I will retain the model or recalibrate the decision threshold. In summary, the key improvements came from meaningful feature engineering based on financial risk logic, proper handling of class imbalance, LightGBM and CatBoost Ensemble, careful validation using stratified cross-validation, and threshold optimization guided by business implications. These steps enables us to achieve a final F1 score of 0.8626 while maintaining a well-fitted and stable classifier. Thank you.